Greetings. These are the lecture notes for Food Science 571, Food Process Engineering Technology. This is your instructor, Dr. Barrett Vaughn of the Department of Food and Nutritional Sciences. This is the first lecture of Topic 1, Problem Solving, and there are 4 lectures in this series. We start this lecture with asking the question, what is food engineering? Food engineering is application of principles and practices of engineering to food processing systems. It is also an analysis of equipment and systems used to process food on a commercial production scale. But where we're really looking at it's a quantitative description and presentation of food processing and related operations. When we talk about food processing, we like to describe the different steps that we take to process food as being unit operations. The unit operations that are most common fall within 4 different categories. There's ambient temperature processing, that is to say, processing at room temperature. There's processing by application of heat, processing by removal of heat, and then there are also post-processing operations. Under the category of ambient or room temperature processing, you have raw material preparation, size reduction, mixing and forming, mechanical separation, and fermentation. Under the category of processing by application of heat, which is very common since we need to add heat to many foods to stabilize them, to cook them, to change their form, you have processing by application of steam or hot water. You have processing by application of hot air. You have heat processing using hot oils. And you have heating by irradiated energy. Also under the processing by removal of heat, which is almost as common, you have chilling and controlled atmosphere storage, you have freezing and thawing, and also you have freeze drying and freeze concentration. Following those kinds of processes, you have post-processing operations such as coating, enrobing, battering, breading, packaging and packaging materials, filling and sealing of containers and shrink wrapping, and also you have materials handling and process control. We start with this course with giving you the kinds of tools that you need to really complete this course. This course is primarily an applied mathematics course, and we'll go through in this chapter a number of basic tools that you'll need to be successful in terms of making sure that your calculations are correct. Primarily this should be a review, and the next unit we really will get into some new material. But we start now with problem-solving tools in terms of significant digits, which means that all exact figures are followed by one doubtful figure. You have 4 different kinds of significant digits on the screen right now. You have exact figures that result from counting or because they correspond to definite marked divisions on a scale. You have the doubtful figure, which is figure obtained from estimating between scale divisions. You have zeros at the left-hand end are not included in the number of significant figures. However, zeros at the right-hand end are included only if they are considered to be exact, regardless of the position of the decimal point. As we continue with rules that govern significant digits, we also note that zeros after a decimal point are not needed to place the decimal point. They should be included only if they are significant. Also, unless a magnitude has uncertainty specifically stated, for example 2.2 plus or minus 0.01 centimeters, the uncertainty in the value of any continuous variable corresponds to plus or minus half a step of the significant figure stated. Here we show a number of significant digit examples. In the first example, you see the number 2.2. Because of where the decimal is placed and the fact that you don't have a 0 after the second 2, the tolerance is 2.2 plus or minus 0.05, which is the half step that was talked about earlier. Therefore, you have two significant digits. By the same token, if you have a 0 after the 2.2, the tolerance becomes 2.20 plus or minus 0.005. Because you have the 0 there, you have three significant digits. Also, an example of this being pi, of course, you see that there are 5 numbers that are given and that the tolerance is half a step past the last significant digit. And there are 5 significant digits. In another example, when you see perhaps a pure number that's just given as a number like the example there, 2, you have 2 plus or minus 0.05, that half step, but your significant digit is only 1. In the case that you see next, which is 0.0030, you see that that has to be a half step after the last 0 after the 3, and therefore there are two significant digits because you have that 2 there. The next 3 examples you see where the tolerance itself has to dictate the amount of significant digits that there are, and therefore that tolerance must be given for you to determine how many significant digits there are. You have 2200, however, depending on the tolerance, that will dictate the number of significant digits, which on the screen you see 2, 3, and 4, which all correspond to what the half step or where the half step actually is located. On this slide, we start with another basic concept called rounding off. And primarily, we'll go through these rules. Precision of results from any arithmetic calculation depends upon the precision of the least precise number used in the calculations. In the example that you see, the least precise actually is the first digit after the decimal, regardless to how many different significant figures that you actually have. In this case, the 2.2 really dictates how many significant digits you have, and that's why the answer is actually 6.9 instead of 6.9115. There's a process of discarding insignificant figures is rounding off. And note that a series of numerical calculations should be carried out with several significant digits, and the final answer should be rounded to an appropriate number of significant digits. For example, 10 divided by 3 can be 3.3333, but you need to definitely round that down eventually. You can use an extra figure in a result if the term with a few significant figures began with an 8 or a 9. And also you have to recall that when the first figure of a final result is 1, an extra significant figure is justified. In this example, you see that there's an additional significant figure justified in the example. Also, when you're finding root, use the propagation of the maximum error. Also, understand that during a sequence of calculations, it's better to retain at least 2 doubtful figures to avoid accumulating rounding off errors. Reduction to 1 doubtful figure is made only for the final result. And one of the things that you have to keep track of is, in these days of very high-tech computers and using Excel and a lot of these different calculators, that even though you're getting an answer that comes out, you want to be sure that that answer makes sense when you finally give the answer that you are submitting. However, the general rule is present calculated results as a minimum of 3 significant digits. And you will learn better in this class if you bring your textbook and calculator to class, so that when we go through these examples, you understand how it is that we're doing it. And now we come to a very integral aspect of this course, the concept of dimensions and units. Dimensions are a physical entity which can be observed and or measured. However, primary dimensions are length, time, and temperature. A secondary dimension involves the combination of primary dimensions. For example, volume is the cube of length. So when we talk about dimensions, those are basic fundamental ways of looking at quantifying things. You have the length, you have the time, you have the temperature, those kinds of things. And those really are what you use to sort of describe certain physical, thermodynamic, electrical characteristics. In contrast, you have a unit, which represents a known standard or quantity. You have different unit systems. You have the imperial, or what they also call British units, and you have SI units, which we also know as being metric. And when we talk about the SI system, you have base units that'll be meter, which is a measurement of length, kilogram, a measurement of mass, second, which is a nearly universal measurement of time. And you have other sorts of measurements for different things. But you also have derived units such as newtons, joules, watts, volts, and ohms, which are really all derived from some of the other basic units. Here are a couple of aspects that you should be sure to observe when working out problems in this class. 1. Dimension consistency. When solving a problem, both sides of an equation must reduce to the same dimensions. Pretty much you need to make sure that when you are setting up your equations that you will write all of the different units that each of the different components have. So be sure that you are writing all of those down and writing them correctly. Also, you have to have unit consistency. Units employed for the dimension should be chosen from a consistent group. You'll find that when you're very diligent about writing down what the units are, that you'll be sure that you're using the right aspect or the right quantity to be able to solve that problem, because it needs to match the other side. Also, you look at unit analysis, which is critical to solving many physical problems. By and large, if you make sure that you're using the right units, you can be sure that you're going to get the final answer correct, because you've included everything that pertains to it. You also have unit factors used for conversion of units. Ratio of actual value is 1. Don't be confused when you see a number of unit factors. Some of them may have gram over gram or grams per second over grams per second, but by and large they're placed there really to be able to expedite the solution of the problem, and also they physically make sense. Also, you have unit conversion, which is the combination of numbers and units in the numerator of a unit factor is equal to the combination of numbers and units in the denominator. Basically, everything should be able to cross out as they say. You want to see Appendix A for general information on the SI units, and also are listed are a number of very important appendices that give you common, basic, and derived units, as well as the prefixes and conversion constants. I encourage you to look at those tables right now and review them so you're familiar with them and where they're located in the book. Also important is measurement, which is comparison of unknown with the known. The result of comparison expressed in multiples of a known quantity. When you record a measurement, 3 parts, a rod is 1.18 meters long. You have the dimension of the quantity, which is the length. You have the unit, which represents the known or standard quantity, which in this case is the meter. And then the number, the ratio of the measured quantity to a standard quantity. So for example, you have the dimension, which is what it's actually being measured, length, time, mass. You have the unit, which is foot, inches, meters, kilograms, pounds, stone. You also have the number, which is actually the measurement that you have, which plays into what it is that you're trying to understand. And you also have 2 different aspects of the numbers that you have. You have accuracy, which is closeness to the correct or true value. And you have precision, which is indication of the number of significant digits used, which deals with discrimination. And there's a section in the book that really explains the difference between accuracy and precision. You can be accurate without being precise. You can be precise without being accurate. But what we really are trying to get to is where we actually are displaying both accuracy and precision. And that has a lot to do with how it is that we're calculating a lot of these problems. So I encourage you to find that section in the book and review it. Also, you need to understand random error, which is the degree of reproducibility among several independent measures of the same true value. When you have systemic error, it has a definite identifiable cause, which can be something going wrong with an experiment that continues to introduce error. That could be if you have a scale that's not calibrated correctly. Everything could be plus a certain amount or minus a certain amount. There's high precision when the random errors are small, and there's high accuracy when systemic and random errors are small. And the standard deviation and standard area of the mean is a measure of precision. You may go over what these quantities are in a statistics course. For the purposes of this course, we won't be reviewing this material. Throughout this course, with it being an applied mathematics course, we will be dealing with algebraic equations. So we should go over a number of the principles that deal with these equations. They're a statement of equality between one or more expressions involving variables and constants. There's a manipulation of y is equal to ax plus b, for example. You, at this point in time, with your prerequisites, should be able to solve problems that are set up this way. You should be able to perform simple algebraic manipulations. You should also be able to interpret graphical representations of the equation if they are graphed out. Now, the use of Excel and graphic calculators is encouraged, but you still need to understand what those graphs really mean. You should also be able to solve equations for unknown parameters. That would be if in the above equation, if you were given y and you were given a and b, you should be able to solve that equation for x. You will be solving equations for unknown parameters throughout this course. Also, you should know common formulae used in food engineering applications. One of the benefits of this class is that the class will be open book, or the test examinations will be open book and open note. However, you need to really know exactly how you are applying a lot of this content. There will be examples where you have exponents, which is raising a constant or variable to a power. We will also use logarithms, which below you see some of the rules that govern logarithms. They will not be used extensively in this course, but you should still understand some of the rules that are listed below. And also, you need to have calculators now for log calculations. You can use logarithm tables, but they're relatively cumbersome. I wouldn't suggest that you attempt to use them. This brings us to the end of our lecture on problem solving, lecture 1 of 4. If you have any questions, please feel free to contact me on my email address that's given in the syllabus. Also, you'll be wanting to read chapter 1. Thank you.